All right, let's dive into a really critical part of the Go compiler. This is the moment where it stops just reading your code and starts to actually understand it. And to do that, we're going to imagine this whole process is like a tough exam, with the compiler as a super strict teacher grading your code line by line. And this quote, it just nails the problem we're talking about. See, after the first stage, parsing, the compiler has a blueprint of your code. It's called an abstract syntax tree. It knows the grammar is right, it sees you got a function that calls another function with some variable, but it has absolutely no idea if any of it makes sense. It doesn't know what FMT is, what println does, or if you're even allowed to do what you're trying to do. And that's where this whole stage comes in. We're looking at name resolution and type checking. This is where the compiler figures out the meaning and the logic. Think of it like a gatekeeper. It's making sure every single piece of your program isn't just written correctly, but that it's also logically sound based on the strict rules of Go. So to make this super clear, we're sticking with our big analogy. The compiler is a teacher grading an exam. We'll look at the ungraded paper, then go through the 4 main questions the teacher asks to check your work, and finally, see how it all leads to a final grade that decides if your code passes or fails. Let's get started. So just picture this. Your Go code is like a completed math exam. You've handed it in, and now the teacher, our compiler, is sitting down to grade it. But they're not just looking at the final answer at the bottom of the page. Oh no, they are going through every single line, every variable, every calculation to make sure your logic holds up from beginning to end. And you know, this teacher is super methodical. They ask a series of questions in a very specific order. First up, they have to figure out every single name you've used. Then, they check if what you're doing is actually valid. After that, they check any promises you made, figure out abstract stuff like generics, and then, at the very end, they do one last pass to clean things up and check for any sloppy, useless work. These 5 steps are basically our roadmap. First up is question number 1, which is all about name resolution. This is pure identification, and it is the absolute foundation for everything else. Before the compiler can check if your code is correct, it first has to know what every single word you've written actually is. So the very first question the teacher asks when looking at your paper is simple and to the point. Who are you talking about? Every time you use a name, a variable, a function, a package, the compiler just stops and asks this question to make sure there's no confusion. Okay, look at this line of code. We've all written it a million times, right? fmt.println x. To us, it's just automatic. But for the compiler at this point, it's a bunch of total unknowns. It has to figure out every single name, fmt, println, and x. It can't assume a thing. So the compiler starts a little investigation. It sees fmt and immediately goes, okay, let me check the import statements at the top of the file. It finds import fmt. Great. Then it looks at the precompiled info for the fmt package and asks a really simple question. Is there an exported thing called println in here? If the answer is yes, awesome, it makes the connection. If not, boom, compilation fails right there. It's just a simple check. Does this thing exist or not?
Okay, hold on. This might make you wonder. If the compiler has to look up info about FMT to check my code, does that mean it has to compile all my imported packages before it even looks at my own files? It's a really good question, and the answer is actually key to why Go builds so fast.
The answer is a big, resounding yes, and it's all thanks to something called separate compilation. See, when you build your project, Go compiles your dependencies like FMT first, or more likely, it just finds a cached version. This process creates the machine code, but also a much smaller metadata file, kind of like a cheat sheet. So when it's time to compile your code, it only needs to read that little cheat sheet to do its checks. The actual stitching together of all the code happens way later, in the linking phase. So, yep, imports get ready first. Okay, so the compiler now knows what everything is. It's connected FMT to the format package, println to that function, and x to a variable you declared. Now comes the second and really crucial question. Are you using them correctly? This is type checking. The teacher's second question is a bit stern. Are you allowed to do this? This is where Go's famous type safety is enforced with an iron fist. It's not enough to know what things are. Anymore, now the compiler has to make sure that every single thing you do follows the language's strict rules. This is what stops a huge category of bugs before your program can even run. And this slide shows a textbook example of what the compiler is hunting for, a classic type error. In our code, we declared a variable x as an integer. Then we tried to add it to the string hello. And because of that last step, name resolution, the compiler already knows for a fact that x is an int and hello is a string. The compiler's logic here is fast and unforgiving. It looks at that plus sign, checks the Go language rulebook, and asks, hey, is there a plus operation defined for an int on the left and a string on the right? The answer is a hard no. And because this happens at compile time, the program is just rejected on the spot. You get a clear error message in your terminal way before that code could ever run and cause a weird crash. This is the heart and soul of type checking. All right, moving on to question 3. This one gets a little more abstract. This is where the compiler checks the claims, or you could say the promises, that you make in your code. And in Go, this is pretty much all about interfaces. So now the teacher looks at your code and asks, do you actually keep your promises? An interface in Go is basically a contract. The io.reader interface, for instance, is a promise that any type that wants to be a reader must have a read method with a very specific signature. The compiler's job here is to be the impartial judge, automatically checking if your types actually live up to those promises. This slide shows it perfectly. Let's say we have a speaker interface that needs a speak method. On the left, our person type has that exact method. When we try to assign a person to a speaker variable, the compiler looks at person's methods, finds speak's function, sees that it matches the contract, and says pass. The code is good. But on the right, our person is missing the method. The compiler does the same check, can't find what it's looking for, and just says fail, giving you a clear error. And that is the big idea here. You never have to explicitly write type person implements speaker like in some other languages. It's not about what you say, it's about what your type can do. If it has the right methods to fulfill the contract, the compiler is happy. If it doesn't, it's not. This powerful check is done entirely at compile time, which keeps everything clean and gives you immediate feedback. Our fourth question tackles a newer Go feature, generics. This is where the teacher looks at an abstract blueprint you've made and has to figure out what specific, concrete thing you're trying to build with it every time you use it. So the teacher's fourth question is, okay, what do you really mean here? When you write a generic function with a type parameter, say t, you're not writing a single function. You're basically creating a template. It's the compiler's job to look at every single place you use that function and ask, for this one specific call, what concrete type is t? So let's say you write a generic add function for some type t, and then you call it like this, add int 1, 2. The compiler doesn't just kick the can down the road to runtime. No. Right then and there, during this type checking stage, it does something called instantiation. It basically creates a brand new, specialized version of that function just for integers. It swaps out every t for int, and then type checks that new, concrete function from scratch. That's what makes Go's generics so safe and so fast. And now we've hit the final grade. The teacher has checked all the core logic on your exam. They're now just doing one last pass to simplify your work where they can and to enforce some very strict classroom rules that are all about writing clean code. This slide highlights two famous things about Go. On the left, we have an optimization called constant folding. The compiler sees const x equals 10 times 2 and thinks, hey, I can figure that out right now. So it just does the math and replaces the whole thing with const x equals 20 before the program is even done compiling. And on the right, you see Go's legendary strictness. If you declare a variable like x and then never use it, it's not a warning, it is a compilation error. Full stop. The Go creators decided that unused variables are a sign of sloppy code, so the compiler just doesn't allow it. So, after all of these questions and all of these checks, what have we actually accomplished? Well, this entire multi-step process is all about answering one big question. Is this program valid? Does it make logical sense? And does it follow all the rules of Go? By the time this stage is done, the compiler has a perfect, crystal clear understanding of your code. It knows what every single name refers to. It knows the exact data type of every expression. It has confirmed that every single operation is legal. And it has turned all your generic templates into concrete functions. The program is now proven to be logically sound and safe. This table is the perfect way to lock it all in. Parsing looks at the shape of your code and asks, what's the structure? Then, name resolution takes that structure and asks, okay, what do all these names actually mean? And finally, type checking looks at those meaningful names and asks, are you allowed to use them this way? Each step builds on the last, leading to complete understanding. And if you ever need to explain this in, say, a job interview, here's your golden ticket. This is the one-liner that sums it all up. Name resolution figures out what things are, and type checking makes sure you're allowed to do what you're doing with them. Simple as that. So our code has officially passed the exam. It's been checked, it's been simplified, and it's been proven to be logically sound. But right now, it's still just this abstract idea inside the compiler. The massive next question is, how does the compiler take this perfectly understood, logical code and turn it into the actual low-level machine instructions that a CPU can execute? Well, that transformation, that's the next incredible stage in the compiler's journey.